Okay, let's start the class. Okay, let's start. So, good afternoon, guys. I'm welcoming you guys to Chandu biology classes. So, in this session, we are going to concentrate on the physics topic of IIT JAM, that is work, energy, and power, right? So, this is the topic which we are going to discuss today's class. So, basically work is nothing but something we are doing, like if we have applied force on an object has been displaced in certain direction, right? So, object has been done work, we will say, right now. So, energy is nothing but the capacity to do the work, and power is nothing but how much time it has been taken to do the work, we will say as a power. Okay. The first thing which we are discussing is the work. So, let me consider an object A, and we have applied a force on object A, that is F, and object has been displaced for some distance, that is x. Okay, x. So, work done is nothing but F dot x, or else in some books now they would have mentioned that as S. So, both are displacement, S or x is nothing but displacement, and F is nothing but the force. Okay. So, F dot x, so the formula will be Fx cos theta. So, this is the formula for the work done, right. So, work done is a scalar quantity, it is a scalar quantity. So, that is why we are taking the work as the dot product of force and the displacement. Okay. So, the next one is if theta is less than 90 degree, okay, like the cos theta is there, no, work done is equals to Fs or Fx cos theta. So, we are talking about this theta here now. Okay. Suppose if I take an object A and applying a force in this direction, right, and object has been moved in the same direction. Okay. So, whether the object having objects are doing the positive work or negative work or zero work, the thing I should do, I should check it. So, the thing is like I have applied a force, like the maximum force which I can apply by myself, and the displacement has not been taken place, which is the thing is here I have applied a force in this direction, and displacement either in this direction or in this direction we will talk, right. So, the angle between the force and the displacement is perpendicular, that is 90 degree. And when we are talking about the cos 90, no, cos 90 is 0, right? So this is the cases which we are going to discuss now. The first case is, if theta is less than 90, work done will be positive. If theta is equals to 90 degree, work done will be equals to 0. Suppose if theta is greater than 90 degree, work done will be negative. These are the three cases of the work done. Okay. So these are the three cases of work done. Okay, you can take a note of this. So the next example is, suppose if I take a circular path, okay, and a force which is applied here, no, and let me consider the circle of radius r, and a force is which is considered as centripetal force, we will say centripetal force, and object is moving in this direction. Okay, so if I consider any point, no, and if I draw a tangent for that point, that is my direction of the object. Okay, I am considering this point and now I am drawing a tangent, so this is my direction, so displacement will be happen in this place, right? So the work done for the circular path is always 0. So work done for the circular path is always 0. This is the case. And the same case if I consider for the oscillation of the pendulum, to and fro motion. Okay, so this was my oscillation and the pendulum is going to and fro motion. So tension will be towards this end, right now, away from the body, we will say tension will be always away from the body. So when we talk about the tension, it's always away from the body. So tension will be in this direction and displacement will be in this direction, right? So this is my displacement S or X. So the angle between the force, that is tension, and the displacement is again 90 degree. So in this in such cases, no, like a circular path or a pendulum oscillation, the work done will always be equals to 0. So the two things which we should remember is, it is a scalar quantity which has only magnitude, right? Then SI unit of force is nothing but Newton and the displacement is nothing but meter. So SI unit of work done is, either we can say SI unit of work done is, either we can say it's a Newton meter or else joules. So this is SI unit. Done. We'll go for the next one. So suppose if I take a object, so let me consider object A. So since now we have discussed about only one force and displacement happen. Now like multiple forces are acting on a same object. For example, F1, F2, F3, Fn. Okay, Fn forces. Like these are the forces are acting, then what will be my work done? Okay, so similar only, like work done will be equals to the whatever the forces are acting. No, I should consider every forces and then the displacement, right? So F1 plus F2 plus F3 plus up to Fn into displacement, that is dot S. Okay, so this is my work done for multiple forces. Work done for multiple forces. So if I talk about particular work done for particular force now, so we can write like this. So work done will be equals to F1 dot S plus F2 dot S plus up to Fn dot S. So where F1 dot S is nothing but work done by the first force, F2 dot S is nothing but work done by the second force, so up to work done by the nth force. So the total work done will be equals to W1 plus W2 plus up to Wn. So we'll go for the next one now. Okay. So the next thing is the important points about the work done. So work is defined only over a displacement. So work done happens only when object move. So here we have talked like suppose this is my like a wall, like horizontal, I mean vertical wall is there, okay, and I am keeping an object like this and I am applying a force in this direction. So if I talk about this condition, there is no displacement happened for the object. The same condition, if I take a horizontal floor and I am applying a force in this direction, the perpendicular direction, okay. So here also the force is perpendicular to the displacement, here also the force is perpendicular to the displacement. So since the displacement doesn't happen, I can't say there is no work, like force I have applied but there is no displacement. So there is no concept like instantaneous work, okay, and we have talked about instantaneous velocity, instantaneous acceleration, right. So there is no concept like instantaneous work, okay. So because work needs a finite displacement, not a instant displacement. Like if I talk about displacement, I will talk from this point to this point. I won't talk at that particular point what is the displacement or what is the work done happen, okay. So this is the first point. The second point is for a given displacement, work done by a force does not depends on how much object has been moved, okay. So for this same displacement, work stays the same whether the objects move fast or slow. Like the thing is work done doesn't depends on the time period, how much time it has been taken to complete from point A to point B, okay. Suppose if this point is having distance like 3 meter, okay, and I have applied some X force on that object, okay, and object has been covered from point A to point B, whether it is 1 hour or 2 hour, I doesn't care about the time, but object has been done the same kind of work, no. So if I talk about X force, okay, so work done will be 3x, right now. So x is anything, any number we can consider like 1 Newton, 2 Newton, 3 Newton, etc. Okay. So the work done will be same when I talk about in 1 hour or 2 hour or 1 day also, the same amount of work will be done, right. So it doesn't depends on how much time it has been taken. Yeah, that's the thing. So it is independent of time. So if many forces act together, the work done by the one force does not depends on the other forces. So if the same condition like which we have discussed about multiple forces, so F1, F2 up to Fn. So the thing is, if many forces act together, the work done by one force does not depends on the other forces, right. Like work done for one, I mean force for one, no, this force is there, this force depends on the work done W1. Similarly work done W2 will be depends on the force F2, right now. So it doesn't depends on the other forces. So this is the fourth condition. And the fifth one is the work done depends on the reference frame because displacement depends on the reference frame. So when we talk about a displacement, we are talking about initial and the final position of the object, not the path taken by the object, whether it's an actual path or a shortest path. We will discuss about only the final path, I mean final position and initial position. So similarly when we talk about the work now, so same work also depends upon the reference frame. Okay, we'll go for the next one. Okay, so we'll do a problem now. Fine. So the question is, I'll dictate the question. A particle is displaced from a point A, that is 1, 2. A particle is displaced from a point A. So the point A is 1, 2 to point B, that is 3, 4 by applying a force 2I cap plus 3J cap. The force is given, wait a minute, let me arrange the camera. Yes. Sorry for the disturbance. I hope it's clear now. Right, okay. So the force is 2I cap plus 3J cap. 2I cap plus 3J cap. So find the work done by the F to move the particle from point A to B. So this is the question. So now object has been travelled from point A to point B, okay, and they have given the points as 1, 2 and 3, 4. So it has not moved in either one axis like x axis or y axis. It has been moved in both axes, that is xy axis or yz axis or zx axis, two axes, right now it's a plane. Like a simple word we can say it's a plane, okay. So displacement, no, so displacement is nothing but the final point or final position minus initial position. So final position in I cap 3 minus 1 I cap plus 4 minus 2 J cap. This is the displacement, right. So 2 I cap plus 2 J cap is my displacement. Now work done will be nothing but, so F dot S is the work done. So where, wait a minute, yeah. So where F is 2 I cap plus 3 J cap and S is nothing but 2 I cap plus 2 J cap, okay. So when I talk about the dot products, so dot products, no, so I cap dot I cap will be equals to 1, I cap dot J cap will be equals to 0, I cap dot K cap will be equals to 0. So similarly for J cap also, j cap dot I cap will be equals to 0, j cap dot j cap will be equals to 1, j cap dot k cap will be equals to 0. So similarly for k also. Okay. So when I talk about 2 I cap multiplied by 2 I cap, again 2 I cap multiplied by 2 j cap. So obviously this one I can neglect it out, this is 0 for j cap and I cap. So 2 into 2 is 4, I cap dot I cap is 1. So next one is plus 3 j cap 2 I cap 0, 3 j cap and 2 j cap, it is 3 2s are 6, j into j is, j dot j is 1. So total it is 10 joules. So this is my work done for the given question. Right, we will go for the next one now. Okay, so the next topic is energy. So energy is nothing but the capacity to do work. So the capacity to do work. So this is the first point. So like when we talk about energy, we will come across different types of energy like heat energy, sound energy, like the kinetic energy, potential energy, etc. Right now. So in this particular topic of work energy and power, we will talk about only two energies, okay, like that is kinetic energy and potential energy. So in kinetic energy, like when the object is moving, I can say it possesses kinetic energy. When object is at rest, it is having a stored energy called a potential energy. So two things, one is kinetic energy, next one is potential energy. When I combine these two energies, I will name this as a mechanical energy. So sum of potential plus kinetic energy is called as mechanical energy. So when I talk about kinetic energy, so by motion I can say the energy is by virtue of its motion, I can say it's a kinetic energy. Object is at rest or stored energy, we will say, okay, stored energy is called as a potential energy. Okay, so the formula for the kinetic energy is of mv square, and when I talk about the SI unit of the energies, energy also same, energy also having a same unit, which is joules. So the first one we have discussed about what is energy. Next one we have discussed about what types of energy we are going to deal with in this lesson. Excuse me. And the third one is SI unit of excuse me. The SI unit of energy is joules, the same SI unit as work. Okay. So when I talk about a kinetic energy also having the SI unit joules. When I talk about a potential energy also having a SI unit is joules. Okay. And before that, when I talk about the dimensional formula, no, they might ask you the question, what is the dimensional formula for the work done or energy? So dimensional formula for work done. So when we talk about work done, force and displacement will be there, right? Force is nothing but mass into acceleration. So when I talk about a mass, I can denote this as in capital M. Okay. When I talk about dimensional formula, it should be in square bracket. Square bracket means like the terms m, l, t will be there. M is nothing but mass, L is nothing but length, T is nothing but time. So mass, okay, that is m, and acceleration, no, acceleration is nothing but meter per second square. So meter per second square. So meter is length and the second square, no, per second square. If it is goes upward, no, numerator, t power minus 2. So total term for force will be ml t power minus 2. And when I talk about the displacement, displacement in terms of meter. So again this is L, right? So the total answer for work done, that is dimensional formula, ml square t power minus 2. This is the dimensional formula for work done. So when I talk about the same dimensional formula for energy, the same thing will come, because kinetic energy formula is m into v square, like half mv square, no. So mass, that is m, v square, like velocity is meter per second. When I square the things, no, so meter square per second square. So this is L square t power minus 2. So am I getting the same thing? So kinetic energy or whatever energy, the dimensional formula will be same as the work done, that is m L square t power minus 2. And from this kinetic energy, no, we need a relation for kinetic energy and momentum. So momentum is nothing but momentum, which is denoted by the letter P, is nothing but mass into velocity, mass into velocity. So where I need a relation in terms of kinetic energy and momentum. So they can ask a question regarding like this, like kinetic energy of an object has been increased n percentage, what is the momentum, like it has been increased or decreased. So this was the question in the previous year IIT JAM. Okay, so let us discuss about that question also. So before that, let me derive that kinetic energy is equals to 1 by 2 mass into velocity square. So this one is nothing but like momentum is nothing but mv, right? So in this case, can I multiply by m and divide by m? So 1 by 2 mv square into m by m. So that I can say that 1 by 2 m square v square by m again. So mv the whole square by 2m. So what is mv now? It is momentum. So I can rewrite it as kinetic energy will be equals to p square by 2m. So this is another formula of kinetic energy in terms of momentum. So one formula is half mv square, the other formula is p square by 2m. Done. Now suppose if I consider a system, okay, in the system I will be having n number of particles. So n1, or let me consider n number of particles of different masses, m1, m2, m3, m4 up to mn. So each particle will be moving with different velocities, that is v1, v2, v3, etc. up to vn, right? So when I club together, I'll get a kinetic energy of the system, right? So when I talk about a system will be having a n number of particles. So n number of particles means each particle will be having different masses. So different masses will be having different velocities, right? So when I club together, I'll be having a common kinetic energy, that is, can I write like this? So the total kinetic energy total will be equals to, so 1 by 2 I can say it's a common term, like a constant, right? 1 by 2 will take commonly outside, m1 v1 square plus m2 v2 square plus up to mn vn square. Done? So if I talk about each particle's kinetic energy, it is k1, k2 up to kn, right? So if I take this 1 by 2 inside, no, so of m1 v1 square, which is nothing but kinetic energy 1, of m2 v2 square, which is nothing but kinetic energy 2, of mn vn square is nothing but kinetic energy n. So this is my total kinetic energy of a system, which is having a different masses, like a particle which is having different masses, different velocities. You can take a note of that. So now the question will do. Done? Okay. So the question is, the kinetic energy of a body increased by 21%. Okay. So initially there was a kinetic energy, that is of mv square. Now it has been increased by 21%. What is the percentage increase in the magnitude of linear momentum of a body? So they are asking what is the percentage increase in the momentum. Okay, like they have given it is increased. So I need to check how much percentage it has been increased. Okay, in some question they won't mention that it has been increased or decreased. Okay, but when I see the condition, no, kinetic energy is directly proportional to the potential energy. I mean not potential energy, it's a momentum. Kinetic energy directly proportional to the momentum, right? So when kinetic energy increases, obviously momentum also increases, no? Yes. So we'll see how we'll do that one. Okay, 21%, no? So 21% is the question. It has been increased. So initially there will be some kinetic energy. Kinetic energy 1 will be equals to 21% of kinetic energy 2. It has been increased 21%, which means initially it has been 100% will keep. So now it is 121%. I mean 121. Okay, 121 by 100 will say. So kinetic energy, that is of m1 v1 square. So mass will be same, no? Let me write of m1 v1 square will be equals to 121 by 100 1 by 2 m 2 v2 square. Okay, this is the thing. Now I need to change this in terms of momentum. So momentum is nothing but mass into velocity. So when I talk about here 1 by 2 I can cancel it out, right? 1 by 2 I can cancel it out. So here, no, m1 v1 square into m1 by m1 will be equals to 121 by 100 m2 v2 square into m2 by m2. So obviously when I talk about mass, it is same. No need of calculating the mass. I can write like this: m1 will be equals to m2. Okay. So here I can rewrite this as p1 square by m1 will be equals to 121 by 100 into p2 square by m2. Right. So since m1 and m2 are same, no, I can cancel it now easily. Before that, if you cancel, I can't take in terms of momentum, right? So I can expand in terms of momentum and then I can cancel the remaining terms. So if this is square again, okay. So p1 square will be equals to 121, p1 square will be equals to 121 by 100 into p2 square. So if I take root of 121 by 100 p2 square, na, I will get this one as p1 will be equals to 121 by, I mean not 121, 11 by 10 p2, because 11 square is 121 and 10 square is 100. Okay. So next one is P1 by P2 will be equals to 11 by 10. Okay. Now I need a change in change in momentum, how much it has been increased from initial to the final case. So let me take the terms here, that is -1 and 11 by 10 -1. Why? Because P1 minus P2, the change in momentum, right, by P2 will be equals to 11 minus 10 by 10. 11 minus 10 by 10. So the final thing, how much? No. So it is change in momentum. I will take as it is P1 minus P2 by P1. So P2 will be equals to 1 by 10. 1 by 10. I need in terms of percentage now. So P1 minus P2 by P2 into 100, like in terms of percentage now, will be equals to 1 by 10 into 100. So 0 and 0 will get cancelled. So it is 10% has been increased. 10% increased. Right. So this is the answer for the given question. So initially kinetic energy was 100%, it has been increased by 21%. Now the momentum initially was 100%, now how much it has been increased? It is increased by 10% now. That is the answer. You can take a note of this. Done. The last part, yeah, you can take a note of this. Excuse me, I will arrange the camera. Yeah, it's fine now. Done. Can we go for the next one? Okay. So the next one is, so we have talked about work done by the constant force. Work done by the constant force, which is nothing but W is equals to F dot S or else Fs cos theta. Suppose now we are talking about work done by the variable forces, like a displacement has been happened, okay, from point A to point B, but each point now the force is different. So now what will be the work done? Okay. So the next one is work done by the variable force. Variable force. So the total work done will be equals to integral of from x1 to x2 f dot dx, f dot dx. So this is my work done for the variable forces, variable force. Okay. And one more thing, when we discussed about the motion in a straight line or motion in a plane, no, There we have discussed about the graphs. So when we talk about xt graph, area under xt graph will give velocity, area under velocity time graph will give, that is vt graph will give acceleration, right. So similarly here area under, now suppose if I talk about this is my graph, okay, from this point to this point a force has been applied and a displacement has been taken place. So this is my force and this is my displacement. So the area under the graph always will give the, that is area under the graph, that is fs graph, okay, fs graph will give the work done. The next point is the area under the force displacement graph gives work done. And when we talk about the same kind of graph, suppose so, this is the graph for example, okay. Now from this point to this point work has been done. So let me cover these areas, okay. So the area which is under, under or above, okay, above the x axis, positive x axis, no, will give us the positive work. So this is my f and this is my s. So this one will give positive work and this one will give the negative work, okay. So area under the curve gives the work done, but in that a small trick is there. Above graph will give positive work and below graph will give negative work, okay. These are the conditions for the work done. One is constant, one is variable, area under the force displacement graph. You can take a note of this. Done? Okay. Now we will see the question. So the question is, a force F is equals to 0.5x plus 10. Force F is equals to 0.5x plus 10 acts on a particle. Here F is in Newton and x is in meter, okay. F is Newton, x in meter. Calculate the work done by the force during the displacement of a particle from x equals to 0 to x equals to 2. So during a displacement x is equals to 0 to x is equals to 2, okay. Since this is a variable, no, variable force, na, like if I substitute the value of 1 I will get different force, if I substitute the value of 2 I will get different forces here, right. So I need to get the value of work done now. So what we have known, the formula, work done for the variable force is nothing but x1 to x2 f dot dx, right. So integral x1 to x2, the given is like this is x1 and this is x2, okay. Force is nothing but 0.5x plus 10 into dx. So what is x1 and x2? It is 0 to 2. It is 0 to 2, no, right. So integral from 0 to 2, 0.5x plus 10 dx. Now I need to integrate it, right, integrate it. So I will expand this one. So integral from 0 to 2, 0.5x dx plus integral from 0 to 2, 10 dx, 10 dx, right. So 0.5, it's a constant, no, it's a constant. I will keep as it is 0.5 as it is, no. So 0 to 2, okay, 0 to 2, wait a minute, okay, so 0 to, yeah, so 0 to 0.5 from 0 to 2, okay, so x integration is x power n by n plus 1, right. So when I integrate the things, no, x power 1 by 1 plus 1 will come, na. So obviously like n plus 1 by 1 plus 1, so x square by 2, right. I will write the integration formula, x power n is nothing but x power n plus 1 by n plus 1. So when I differentiate it, n into x power n minus 1, okay. So from 0 to 2 plus, so integral of a constant with respect to some variable, na, that is dx, x is the variable, so I will write that as 10x from 0 to 2, that's it. So now I take this 0.5 inside, or I can keep as it is, okay. Now I can take this upper limit and lower limit inside. So 0.5 upper limit is 2 square by 2 and lower limit is 0 by 2 plus 10 I will keep outside, upper limit is 2 and lower limit is 0, okay. So now it is 0.5 4 by 2 minus 0, total term will become 0, no, 0 by something will be 0 plus 10 into 2. So now it is 0.5 into 2 plus 20. So this one will become 1 plus 20, which is 21 joules is the answer for the given question. So the question was F is equals to 0.5 x plus 10 and the displacement happened from x1 is equals to 0 to x2 is equals to 2. So find the work done. So whenever we are getting a variable, any constant terms in force, no, that is a variable force we will say. For example, no, if I substitute the value of 0, it is 10. If I substitute the value of 1, it is 10.5. If I substitute the value of 2, it is 11. Okay. So I should consider the variable force formula. So integral x1 to x2 f dot dx. So I have taken the condition and we have solved the problem. That is 21 joules. Okay. So I hope you got some points regarding the work, energy and power, right? So we have done some part of work and some part of energy. So in upcoming classes, no, we will do some more problems related to work as well as energy, and we will see some kind of energies also, like a potential energy in a spring. Okay, potential energy we should see, and spring energy. Okay, and what is the energy stored in the spring also we will see in that class. Okay, then we will see the topic like what is conservative forces, non-conservative forces, then work energy theorem. So with that topics, no, we will end the work energy power. Yes, one more topic, that is power is there. Okay, after work energy theorem, power topic is there. So power is nothing but work done by times, and we will see that also, like some problems in power also. Okay, so with that topics, no, we will complete the work energy power. Okay, topics, right? Okay, thank you guys, we will meet in the next class.